right, as we begin today, going to start with practice exercise 67, some basic probability questions. Remember, we want to write probability as a ratio. And of course, we always reduce ratios. You've got the little picture there. You've got a little reminder of how probability works, number of things you want over number of things possible. Go and get started. Exercise 67, you may begin.
Your quiz coming up tomorrow, so as you reviews, pay very close attention. Jot things down if you need to. Of course, pay good attention to today's lesson as well. Alright, lesson 19, going forward.
Let's go ahead and take a look at our answers together. And Ethan was first. Ethan, what's the probability that the pointer will stop on 7?
1 over 10.
1 to 10. That's one desired outcome is a 7 out of 10 possible, so 1 to 10. What's the probability the pointer will stop on a 3 or a 9?
1 to 5.
1 to 5. There's two possibilities here, 3 or 9 out of 10, so 2 to 10 reduces to 1 to 5. What's the probability the pointer will stop on a perfect square?
1 to 5.
It is not 1 to 5. Genesis, you were second. Are you perfect on the first two? You are not. Jamie, you were perfect on the first two? No, you were not. Audrey, you were next. Were you perfect on the first two? What did you get for the third one? 1 to 5 also. Kendall? How many perfect squares are on there, class?
I thought there was 2.
Well, 1 squared is 1,
Oh.
2 squared is
1.
4, and 3 squared is 9. So there's 3 of them on there. 3 to 10 would have been the probability. What's the probability the pointer will stop on an even number? Let's go to Genesis.
1 to 2.
1 to 2. There are 5 even numbers. 2, 4, 6, 8, 10 out of 10. So 5 to 10 reduces to 1 to 2. What about the probability this pointer will stop on a prime number? Jamie?
2 to 5.
2 to 5. 4 prime numbers. 2, 3, 5, and 7 out of 10. So 4 to 10 reduces to 2 to 5. You don't get candy. I'm just tossing you candy for no reason. Well, you're already late, so you might as well go and see me after class. All right, go ahead. It's 5 minutes. You get 5 minutes on the freebie. All right, so go ahead and pass those forward if you would, please. And take your homework out. And turn your notebooks to the Theorems Corollaries section. Turn your notebook to the Theorems Corollaries section. Theorems Corollaries section. And we'll take a look at those here in just a moment. I want to review a term that I taught to you on Friday. It's really what all of your theorems that you were copying out had to do with, and that's this idea of a locus. Audrey, reminder, what is a locus anyway? L-O-C-U-S. We asked several random miscellaneous locus problems really to do with this classroom in our last lesson. You know what a locus is? Kendall, can you help her? Anyone remember without looking it up?
A group of points.
It is a group of points, good, but it's not just any group of points, it's a group of points that satisfies a particular condition, right? Now we said there's two qualities of a locus, two key characteristics. We said, first of all, a locus class must be inclusive. That is, that any point that satisfies the condition must be included. You cannot come up with a locus that would exclude anything. So remember we said if we want to know 5 feet from the wall, well, I can't just say, okay, this point, because what about this point right here? This is also 5 feet from the wall, right? So we said any point that satisfies the condition must be included. But we said a locus is also exclusive, in that if it doesn't satisfy the condition, you better not include that in the locus. So we're looking for that which is both inclusive and exclusive. Anyone remember what the plural of locus is? If we wanted to have two different locuses, it's not locuses, it is?
Loci.
Not loci, loci, soft C sound, but loci. And we'll be working with multiple loci moving forward. For now, though, you've got your notebooks open to the theorems corollary section. You copied out theorems 47 to 52, and I think there was a corollary worked in there as well. Good. 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 And good. And your corollary you went ahead and did separately. All right. Let's go ahead and we'll look at those in just a moment. Keep your notebooks out, but while you've got your notebooks out, also get your textbooks out. Just set your textbook on top of your notebook. Want to look at just a few more locus problems, but having copied out those theorems, that may help you to process some of these other locus problems here that we didn't have a chance to get to in our last lesson. I'm going to wrap up last lesson very quickly here. Page 174 in your textbooks. Page 174 at the top of the page. Of course, this is where you started copying out those fundamental locus theorems. At the very top of the page, exercise number 5. Go ahead and read that locus question for us, Quentin.
A man rows a boat up a stream, keeping the same distance from either shore. What is the path described by the boat?
All right. Now, the question is, what does the stream look like? For instance, if the stream is something like this, where it's pretty much just kind of going straight, well, if he keeps the same distance from either shore, then he'd be right about there. We would pretty much get class A straight line, right? That runs down the center. Now, if the shore lines were straight, then this straight line would run parallel to the straight lines. But assuming that this creek were curved or something, then keeping equidistant from either shore would basically be, he would simply be transversing the path of the stream, if you will. But again, maintaining equidistance from the shoreline, so right in the very middle, tracking that same path. But again, if it were straight lines, shorelines, for instance, Chattahoochee's not perfectly straight, but for a large section of it, it runs almost straight line, then it would be a parallel line to the sides of the stream midway between them. Question?
Say that the path was curved like that, when each point be parallel to the side?
Well, you'd almost have to say that the tangent to the curve would be parallel to the tangents of the other curve. I guess if you really wanted to get technical about it, but since we haven't really gotten into tangents on curves yet, that's more of a calculus concept. Certainly, I wouldn't actually go there that far. Let's see, number 6. Here's one that's a little bit easier for us here. Chris, go ahead and read number 6 for us.
What is the locus of the center of a train wheel that as the car moves along the track?
Okay, so we've got train track, okay? So you've got the little railway ties, right? And then we've got the track that sits on top of the railway ties. And then we've got the wheel of a train car, and there's the center of the wheel. Now, as the wheel is rolling, what's going to be true about the center of the wheel?
It's not gonna move.
Well, it better move. I mean, if the center of the wheel stays here and the rest of the wheel goes off without it, that could be a little...
It's gonna move at the same point.
So it's not going to be I mean, it will be spinning in a sense, but if you're just watching the center, it just sort of moves along, right? So what would be the locus of all points that the center of the train wheel could be? Okay, it would be a straight line, parallel to the track. Well, I mean, this is a straight line parallel to the track. This is a straight line parallel to the track.
Equidistant from the outside of the circle? It'd be a circle, obviously.
It would be. I thought we said it'd be a straight line.
Be above the track.
It would be above the track. Okay, so that definitely rules out lines below the track, right? Because if the wheel is below the track, we've got some real problems. Okay, now on a roller coaster, maybe not, but trains generally do not function as roller coasters. Okay, so yeah, it would have to be a straight line, parallel to the track, above the track, but how far above the track?
The radius.
The radius of the wheel, right? Whatever the radius of the train wheel is, that distance above the track. Good. Great job, Quentin. Star of the show on that one. All right, the rest of you jump in and steal the show back. On number 7, let's have Kendall read it for us.
Where are located all houses that are 2 miles from your school building?
All right, so obviously our school is in a residential area, not a commercial area, so there's houses everywhere. But here is school. And we want to know where would be houses 2 miles away. House. These aren't very well built houses. House, big house, because there's big houses every now and then. House, long house. Okay, but if we wanted all the houses that were 2 miles away, for instance. Maybe this one is 2 miles away. Maybe this one is 2 miles away, but this one's not, and that one's not, and this one's too far, and this one's too close. Maybe this one's 2 miles away. Maybe that one's a little bit too far. But what if I wanted all the houses 2 miles away? Where would they have to be?
Equidistant from school.
Well, obviously 2 miles from the school, but what would that give us if we were to find every single house that was exactly 2 miles from our school?
Circle.
It would end up being essentially a circle, wouldn't it? Tell me about the circle.
The school is at the center point.
The school would have to be the center of the circle.
And the 2 miles is the radius.
2 miles would be the radius of the circle. Good. Hey, there we go. Ethan jumping in there. All right, though I think Quentin still got it started with circle, so he shares in the credit there. But Ethan jumping a piece of that credit. All right. Number 8. Go ahead and read that one for us. Genesis.
Where are located all towns that are 20 miles from your town?
All right, so we've got Alabama looks something like that, and then Georgia kind of looks something like that. Of course, Florida comes down there like that. Okay, so Columbus is right here on the border of Alabama, Georgia, and about halfway up the state. And so there's, Opelika is a little bit more, right about 20 miles away, and Eufaula is about 20 miles south, and then I think Hamilton's closer than 20 miles, but Macon's a little too far. But anyway, if we were to find every town that's 20 miles away from Columbus.
Another circle. Another circle. 20 miles is the radius.
Circle.
20 miles is the radius.
20 miles is the radius. Now, there would be places of the circle that weren't occupied by towns, but any town would have to be on that circle, wouldn't it? So a circle, 20-mile radius.
Columbus is thy center. And
Columbus would be the center of the circle. Number 9. Read that one for us, if you would, Ethan.
Where is the locus of the end point of the hour hand of a clock as the hand moves around the dial?
All right, so the locus of the end point of the hour hand. So we can turn around and look at the clock there. Normally I tell you don't look at the clock. Now I'm telling you to look at the clock. So the end point of the hour hand, now it moves very slowly, right? But the end point of the hour hand would make a circle, okay. Tell me about the circle.
It's congruent.
It would be concentric with the outer rim of the clock, right? Meaning that its center would be the very center of the clock, where the axle point would be. For instance, have you ever seen one of those clocks that kind of has a base and then it's kind of a dome shape, but the clock itself is here? Well, it wouldn't be the center of the clock, it'd be the center of the axle point of the hand, right? So that would be the center of the circle. And what would be the radius?
The
length
12
of
in the
the
hand.
The length of the hour hand. Good, Jamie. All right, so anyway, all of those, though, in a way, built on some of these fundamental theorems that we copied out last night. So notebooks out. You can set your textbooks aside now. Notebooks out. And Theorem 47, go ahead and read that for us, if you would, Quentin.
The locus of points equidistant from two given points is the perpendicular bisector of the line joining the 2 points.
All right, so if I gave you any 2 points, point A, point B, maybe those 2 points are, I don't know, Ethan and Quentin. And I said, I want to find all the points equidistant from Ethan and Quentin. Would I be equidistant from Ethan and Quentin right now, class? No, I'm much closer to Ethan, right? But if I came over here, now I feel like I'm a little too close to Quentin. But if I was right about here or so, I think I feel like I'm about the same distance from both of them, correct? So if I wanted a point equidistant from these 2 points, well, obviously, if you kind of tracked the line between them, the midpoint certainly would be equidistant, correct? But this point wouldn't be. It's too close. This point wouldn't be. Still a little too close. Right about here, though, it would be equidistant, wouldn't it? And if we wanted to keep finding those points equidistant from these 2 points, well, again, imagine drawing the line equidistant from the ends of a line, perpendicular bisector of that line. So really, Theorem 47 is just a restatement of a location theorem we've already had. The perpendicular, I did a horrible job with it, but the perpendicular bisector of the line segment that would join the points would have to be the locus of points there. Theorem 48, read that one for us if you would, Audrey.
Locus of points is an angle equidistant from the side to the line that bisects the
So we have some angle. And for instance, remember we had the 2 walls there. And I said, what would be all points in the floor that are equidistant from these 2 walls? And I said, well, this point wouldn't be. It's closer to this wall than that wall. But right about here is about the same distance. And we said the angle bisector, right, of that angle would be equidistant. Well, that's because equidistant from the sides of an angle has to lie in the bisector of the angle. So the locus of points equidistant from these 2 sides would be this angle bisector, correct? Corollary 48-1. And Chris, read that for us.
The locus of points equidistant from 2 intersecting lines is the pair of given lines bisecting the angles formed by the given line.
I think it should just say the pair of lines bisecting the angles formed by the given lines. Cross out the extra given there. But yeah, if you've got two intersecting lines, well, what's the locus of all points equidistant from these 2 lines? Well, this forms an angle, so it'd be the angle bisector. This forms an angle. Angle bisector. This forms an angle. Angle bisector. This forms an angle. Angle bisector. But because vertical angles are equal, that line that bisects this angle will be the same line that bisects that one. So that's why it says the pair of lines bisecting the vertical angles. Here is a good way to word that. The bisecting the angles formed by the given lines, in parentheses, maybe after corollary 48-1, add that in there, where it says bisecting the angles formed by the given lines, bisecting the vertical angles. So the pair of lines bisecting the vertical angles would be equidistant. This point is the same distance from line L as it is from line N. This point is the same distance from L as it is from N. This point, same distance from N as it is from L. This point, same distance from N as it is from L, right? So all those points would be equidistant from those 2 intersecting lines. Questions on that one? Yes, sir.
So technically you could have like you can have an infinite number of lines coming off because they just keep bisecting the different angles that are formed. So
well, when you have 2 lines, there are only 2 sets of vertical angles, right?
Right.
Right. So for instance, I think what you're thinking of is, well, what if you had a whole bunch of lines? Call it A, B, and C. Well, you'd have to first, well, what's the locus of points equidistant from A and B? Well, that would be these 2 angle bisectors equidistant from A and B. But they're not the same as equidistant from B and C or equidistant from A and C.
But wouldn't there be also an angle bisector of A in that one you just drew?
Well, no, but that wouldn't be equidistant from these 2 lines, right? Those 2 lines would just be that angle bisector and that angle bisector. Yeah, that's okay. All right, Theorem 49. Read that one for us, Jamie.
The locus of points equidistant from the two parallel lines is the line parallel to each of the given lines and midway between them.
All right, equidistant from two parallel lines. So there we go. By the way, I do want you to notice something. I should have mentioned this on the very first one. Notice how I drew my locus as a dotted line. Okay, that's how we'll show a locus set, is as a dotted line, like an auxiliary line, for instance. So the locus is drawn dotted. So here, if I've got two parallel lines, equidistant would fall in the middle. But there's a whole lot of points in the middle, and we end up with a straight line parallel to the given lines, midway between them. Make sense? Okay. That's a good one to memorize word for word. Put a star next to 49. It's a harder one to memorize, but the wording is very picky there. The line parallel to the given lines, midway between them. We can't just say it's a line between them, because that's a line between them. We can't just say a line parallel between them. That's a parallel line between them, right? Parallel midway between them would be equidistant from those two parallel lines. Theorem 50. Ethan, read it for us.
The locus of points a given distance from a given line consists of two lines, one on either side of the given line, each parallel to the given line and the given distance.
All right, so here I've got just one straight line, and I have some given distance from this line. Well, we understand to maintain that same distance, I'd have to have a line that's parallel to the given line, that given distance away. But, unless it's a train wheel that stays above the tracks, not below the tracks, I might also have that same given distance on the other side. So it's two straight lines, each parallel to the given line, on either side that given distance away. And I think we talked about that with equidistant, or 2.5 feet from Jamie's row. We said, well, there's this row and there's this row, correct? On either side could both be that distance, but they would be parallel that given distance away on either side. Theorem 51. Go and read that one for us, Genesis.
The locus of points, a given distance from a given point, is the circle described with the given point as center and the given distance as radius.
There we go. And this kind of goes back to that example of the school and houses 2 miles away, or the town 20 miles away, right? So if we wanted this particular distance from this particular point, well, that point's that distance away, right? But that point is also that distance away. Well, what if you wanted all the points? Well, you'd end up with a circle with the given point as center and the given distance as the radius. Okay? So, again, school is center, 2 mile radius. Right? So you'd name what the center would be, what the radius would be. And then Theorem 52 is actually not one you're going to have to memorize, because we're not going to use it that often, but there's discussion here. Kendall?
The locus of the sectors of all circles tangent to a given line at a given point is the perpendicular to the line at that point.
So here the idea is, we talked about tangent circles, right? Circles that are tangent to the same line at the same point. Well, if I were to pick this line at this point, there's a little circle I can make tangent right there. Or I can make a bigger circle. I can make a bigger circle. I can make a really big circle, pretend it's an actual circle. But what would be the locus of the centers? Well, there's a center, there's a center, there's a center, there's a center. What would be the locus of all the centers? Well, since the radius to this center is perpendicular, and the radius to this center is perpendicular, well, there can only be one perpendicular, so it's got to be the same line, right? So the locus would end up being this line that's perpendicular, right? But I could also, of course, have a circle on the other side. So its center would also lie in that perpendicular. Okay? So the centers would be lying in the perpendicular at that point. Questions on Theorem 52. That said, as I said, that one's not going to be used quite as often, so we won't have to memorize that. But the first 6 that we discussed, we need to have memorized. Go ahead and close your notebooks for now. Go and have out some paper and a pencil. And let's see how your short-term memory is. And we're going to get these to long-term memory. Let's see how your short-term memory is. Let's just practice with these. Make sure we get these down, but especially give you a chance to think through the wording. Memorization is good, but if you can think through the wording, that would help you memorize. That would help you memorize the wording even better. So let's take a look at this. I want you on your paper to draw two lines parallel to each other. Draw two lines parallel to each other. I suppose you could use the blue lines on the paper. I want you to draw the locus of all points equidistant from those two lines. Draw on your paper the locus of all points, again using a dotted line to draw, the locus of all points that would be equidistant from the two parallel lines. Now, think through. How would you describe to me what you drew? Think through. How would you describe to me what you drew? And we're going to go to Kendall first. Kendall, how could you describe to me what to draw here? Start by telling me what shape you drew.
Straight line.
A straight line. That's always how you want to start the description of a locus. Just tell what shape you drew. She drew a straight line. Just one, correct? One straight line. Now, Kendall, tell me how to draw the straight line.
It's midway between the parallel line.
Okay, it's going to be midway between them, and in order to stay midway between them, it's going to have to be...
Equidistant.
Well, that's what I said. I used the term equidistant. You don't want to use that term in the description, but it's going to have to run parallel to them. Good. So that's kind of what we'd be looking for then as far as a description. I'd be looking for you to tell me you've got a straight line, that it's parallel to the given lines, and that it's midway between them. Three things we'd be looking for in that description. How many have this sketch on your paper? Does it make sense how to think through how to describe it? All right, go ahead and draw an obtuse angle on your paper. I want you to draw for me, or sketch for me, the locus of all points equidistant from these two lines. We're not going to have to do a construction or anything, so it doesn't have to be exactly perfect, but it should look pretty close, and of course you'll be able to describe to me what to draw, so that way if there's any ambiguity as, well, what is that drawing? You know, ever had that with a little kid, draws a picture for mom, and mom's like, boy, that's very good. What is it? We get that with Chloe sometimes. Usually you're supposed to try to guess what it is first, but if you get it wrong, like the kid's feelings are hurt, so usually I'm like, oh good, show that to mommy, you did great. Mommy's like, oh, I told her to show it to you. Let's see, what has she been playing with lately? Anyway, all right, so what did you draw, Audrey? The angle bisector. Very concise, easy way to put that one, isn't it? Right? So the angle bisector, how many had an angle bisector drawn on your paper? Good. Go ahead and draw any 2 points. Draw any 2 points on your paper. I want the locus of all points equidistant from those 2 points. All points that would be equidistant from those 2 points. And Chris, what did you draw?
Straight line.
You drew a straight line. Good. What does the straight line look like?
It's in between the 2 points.
It's in between the 2 points.
No, like it's like a straight vertical line.
It's a straight vertical line, like this.
Yeah, it cuts through both points.
So all of these points are equidistant. So this point is the same distance here as it is from there.
I should have gone with the midpoint.
Okay, the midpoint certainly, that would be the only point on this line, wouldn't it? That would actually be equidistant. So if you were to draw this line, maybe we'll just draw it real lightly here. The midpoint would be a point in the locus, right? But what about every point in the locus, Quentin?
Straight line from that point.
A straight line from that point?
From the,
I don't know, this looks closer here than it does there.
a straight line that's perpendicular to the other line.
Ah, so perpendicular through the midpoint? So a straight line perpendicular to a line joining the points through the midpoint, or better yet, Chris, the perpendicular bisector of the line that would join the points. Good. Do you necessarily have to draw the line that would join them? No, but this it helps to see that the perpendicular bisector is actually perpendicular. Okay, so the perpendicular bisector of the line that would join the points. Though I wouldn't mark him wrong if he had said the straight line through the midpoint of the line joining the points that is perpendicular to that line. I mean, it's a long way to say it, but it's not a wrong way to say it. Okay. Questions on that one? Draw just one point and draw a line segment, just a little segment, label it D for distance. I want all points, that distance, whatever you drew, from that point that you drew. I want all points that are that distance you drew from that point that you drew. Yes. You want redemption?
Yes.
All right, Chris wants some redemption here. Chris, what did you draw?
First, I wrote the points, the distance you gave me, and I marked off from the point I drew a circle around it.
Okay, a circle, right? So that's the first thing, is what shape? It's a circle. And you said the circle needs to be...
It needs to have the radius of the distance.
Good, this distance is going to have to be the radius of the
The
circle.
point at the center.
And the points as the center. Good, now if you left that out, I'd say, well, is this the locus? Because there's the distance as radius, right? But somehow, this point doesn't look the same distance from this as this point does. And this point certainly looks further right. But if the given point is your center, and that given distance is radius, then we've got a locus that looks like this. How many drew this? All right, questions on that? Is that, okay, you're just playing with your hair. Okay, I saw a hand out of the corner of my eye going up. I want to make sure I didn't leave you out. All right, go ahead and draw two parallel lines. I already did this one. Never mind. Don't draw two parallel lines. Draw two intersecting lines. We'll do the other one. Draw two intersecting lines. I want every single point that would be equidistant from those two lines. We'll call one A, we'll call one B. I want all points equidistant from A and B. All points equidistant from A and B. Did you already draw? Wow, that was quick. All points equidistant from A and B. And Genesis is also quick. All right, Genesis, what you got? So what shape, first of all? A circle? Ethan, helper, what shape?
Straight line.
A straight line?
Oh, line. Straight line. Straight line. Straight line. Straight line.
Help him, class.
Hair straight line.
We should have two straight
Oh,
lines
I
here.
didn't have to straight line.
Ah, we should have had two straight lines. Describe, who said two straight lines? I heard a couple of people there. Describe the two straight lines to me, Kendall. Right, so you were actually on the right track at the beginning there, Genesis. There are two straight lines that bisect the vertical angles. So this is a set of vertical angles. We need the bisector of that set of vertical angles, and we need the angle bisector of this set of vertical angles as well. So two straight lines that bisect the pairs of vertical angles. Right? How many had that picture there? I see you had. Why'd you say a circle?
Because when you asked me, you made me think I was wrong.
Oh, you were easily thrown. So I haven't done that too often enough then, apparently. Where I try to make you question everything. And all right, I've not made you immune to my questioning tone yet. All right, questions on this? All right, let's see here. What if we had just to draw one straight line this time? One straight line. And go ahead and use, draw some other little segment, label it D for distance. I want every single point that's that distance from that line. Every point that's whatever distance you drew from whatever line you drew. All points that distance from that line. Let's see, Genesis, do you want some redemption here? She does not want redemption, all right, so she wants help. Let's see, Ethan, can you help?
Need help.
You need help.
Don't we all?
No, a circle. It wouldn't be a circle, would it?
No, it wouldn't be a circle.
But, yeah, all the points were distance from the line.
Right, so for instance, if I wanted this distance away, like that would be that distance away, and like that would be that distance away. Okay, so it would be A line.
A line.
Okay.
Parallel from the
Parallel
given
from.
line. Parallel to the given line.
Parallel to the given line. Okay, so like this is the locus?
At this equidistant from that point.
Equidistant?
Yeah, from D.
Oh, this distance away. The given distance away. So it'd be a straight line. It'd be parallel to the given line. It'd be the given distance away. Like, say something like that with that given distance.
Yeah.
Okay? He's close. Quentin's laughing at you, so Quentin, I'm going to go to you.
Uh-oh.
2 lines.
You could also have that same distance below, couldn't you? So not
Oh,
one,
okay.
but 2 straight lines. Each of them parallel to the given line, the given distance away on either side. Did you catch how to word that? Let me say it again. 2 straight lines, each parallel to the given line, the given distance away on either side. Okay? Now, you are going to have a construction quiz tomorrow, or not a construction, a locus quiz tomorrow, in which you're going to have to be able to draw the sketch and spell out in words what you sketched. So tonight needs to have some time spent studying on how to get the wording down. Hopefully now you know how to make the sketches, right? But practice the wording, looking over those theorems tonight. Let's practice with some things. Go and set your notebook, or just keep that paper out, but turn your textbooks to page 176. Turn your textbooks to page 176, and let's practice with some of these fundamental loci. Page 176. Let's practice with some of these. Numero uno.
Oh no.
Numero uno on page 176. And Jamie, read number 1 for us.
Determine the locus of all points within a circle that are equidistant from the ends of a given chord.
All right, determine the locus of all points within a circle. So draw a circle on your paper. This isn't the locus, so we don't draw it dotted. We start out with some circle. We also start out with a given chord, right? So we have a circle, and we have a chord. And it says determine the locus of all points within the circle that are equidistant from the ends of the chord. Well, the end of the chord would be a point, and would be another point. So you see that really all they're asking for is the locus of points equidistant from 2 given points. This is a memorized locus problem. They didn't say it like a memorized locus problem, but that's what it is. What would be the locus of all points equidistant from 2 given points, Jamie?
The diameter?
It would end up being a diameter, true, but it would be the
Perpendicular bisector.
perpendicular bisector of the chord, which is the line that joins the points. So the diameter. Now, one little technical tweak here. It would be a diameter minus the endpoints. Why not the endpoints?
It has to be a bisector. Oh, no, because they're on the circle.
They're on the circle, and it started off by saying all points within the circle. So it would be the diameter that perpendicularly bisects the chord minus the endpoints of the diameter that were on the circle. But all the other points would satisfy. Do we see how we have to be exclusive there? The endpoints didn't quite satisfy. They had to be excluded. But the rest of the diameter had to be included, right? We couldn't just say the center. I mean, the center is one of the points, but it's not all the points. You understand that? But you also see how it really was just a memorized locus problem. Any question? Yeah.
I mean, I'm thinking about this, it's kind of like China in a way, like the way they settle everything with like population and stuff.
Huh?
You don't understand.
No, I don't. Well, let's move on to number.
Where'd that come from?
Let's move on to number 4. Let's jump over to number 4. Read that one for us, if you would, Chris.
Determine the locus at the midpoints of equal chords of a given circle.
All right. So the midpoints of equal chords of a given circle. So that means we start class with a circle, and we start with a bunch of equal chords. Now think about this. For chords to be equal, they all have to be equidistant from the center. So we draw a chord, we draw another chord, and we try to get a bunch of chords. That one looks a little smaller. Get a bunch of chords that are all equal. Okay, so but I don't just want the chords there. I want to know the locus of the midpoints. So, well, I throw that one on the floor. I've got a midpoint here. I've got a midpoint here. I've got a midpoint here. But what if I were to draw every single chord that's equal to whatever I started with? Like, there's how many equal chords could I draw like this?
4.
An infinite number, right? And if I were to track the midpoints of all of those chords,
You have a
What
lot
are we
of
finding
points.
again?
what's the locus of the midpoints of all equal chords within the same circle? Well, the center isn't going to be on the set midpoint of any of those
Let's
chords.
draw an
Another
inscribed
circle.
circle.
Ah, what?
Another circle.
Another circle. Okay, tell me about the circle.
It also has the same center as the original circle.
How would we say it has the same center, class?
Concentric.
Circle.
Concentric. So we would get a circle, concentric with the given circle. But there's got to be one more detail. The radius, that distance.
All radius.
Well, they would all be equal, but what would they be equal to?
I get a point.
The radius of the circle would equal the
Equidistant.
distance to any one of the chords, right? Because the distance to all the chords is the same, so the radius would be the distance to any one of the chords. So it would be a circle concentric with a given circle, having a radius equal to the distance from the center to any one of the given chords. All right, that was, do you see how to kind of think through, but you also see how to specify, how to word it, okay? Now, again, for now, the wording you have to know are just the ones from the memorized locus problems. But I'm trying to show you how you could word things if they were to get more involved. Does that make sense? So don't panic, just soak in like sponge. All right, let's take a look at number 5 and Kendall.
Determine the locus of all points of the distance from a given circle. When would there be one solution to
All right, so we start with a given
circle?
circle, but we also have some given distance. So draw yourself a circle and some given distance, a little line segment of your given distance. I want all points this distance from that circle.
Does it have to be in the circle or outside the circle?
So what are you thinking, Chris?
Well, I'm thinking if we draw the circle small enough, can't it just be a radius? The distance could be a radius?
Oh, so you're saying what if the given circle had a radius equal to this distance? Oh, that's interesting. Okay, so if we had drawn our circle with this distance as the radius, well, then, but it doesn't say this distance from the center. It says this distance from the circle itself.
But it doesn't say it can't be from the center.
It said from the circle. The center is not the circle. The curve is the circle, right? So I want this distance from the circle.
Can we just draw from the circle and put
Then
the starting
given
from the
circle
sun
would
draw
be-
to
It
the
will be
circle?
another circle that's concentric.
Yes, it would be a concentric circle.
Ah, so we would get a concentric circle, meaning its center is the same as the given. What would the radius be?
2.
The distance plus the radius.
Good. The radius of this concentric circle would be equal to the given the radius of the given circle plus that given distance, wouldn't it? Okay, so, but it says, when would there be one solution when two?
What does it mean by that?
This isn't actually completely inclusive, you know, because I could have had
Another one.
that given distance inside, couldn't I? So in some cases, not all, we're about to get there, you could have two circles, each of them concentric with the first, one outside the circle, having a radius equal to the given radius and the given distance, but the other having a radius equal to
The given distance.
the given radius minus the given distance. All right, so one radius is equal to the sum of the radius and the distance. The other is equal to the difference of the radius and the given distance. But not always will that be true. When could it not be true that you would have two concentric circles?
It's all one.
When would there be only one concentric circle?
When the problem doesn't specify from the center.
Well, never specified from the center, it's specified from the circle, from a given circle.
When you have a boundary.
What?
Hey, at least he's trying. The rest of y'all are sitting there quiet.
When the problem specifies
Everyone's
outside of the
talking
When the problem says it's the radius.
Determine the locus of all points a given distance from a given circle. What if my given distance had been that big? Well, I'm going to take that given distance.
When the distance is bigger than the radius of the distance.
If the distance is equal to or greater than the radius. Because can you have a circle that's that far? Well, you say, well, that's that far from the circle. No, it's not. It's that far from the circle. So if the distance is equal to or greater than the radius, you would only have one circle around the outside. If the given distance is smaller than the radius, you would have two circles, one in and one out. Does that make sense? All right, let's take a look at number 6 and read that one for us. He who dropped protractor. Not that I'm judging because I dropped chalk.
Determine the locus of the center of the circle passing through 2 given points.
They give you a little picture here, right? Circles passing through not one point, so these are not tangent circles. They pass through 2 points. So we've got 2 points, and we've got a circle that goes through the 2 points. Easier said than done. Or we could have a circle that goes through the 2 points. Or we could have a circle that goes through the 2 points. But it says, what is the locus of the centers of all of these circles? If we were to join those 2 points, what would that line be called? Common chord. If we were to join all of the centers with a straight line, what would this line be called? The line of centers. What do we know about the line of centers in a common chord? We already memorized it's the perpendicular bisector, or we should have memorized it. It's the perpendicular bisector of the common chord, right? Theorem 41, Theorem 42, something like that. Okay? So we should have already memorized that. But also, if the center of the circle has to be equidistant from any point on the circle, this point has to be equidistant from those 2 points. And this has to be equidistant from those 2 points. And this has to be equidistant from those 2 points. So therefore, what do we know about all points equidistant from 2 given points? Theorem 47, your first memorized locus problem. Locus of all points equidistant from 2 given points. Perpendicular bisector of the line segment joining the points, right? So it's really just one of your memorized locus problems. All right, we will practice with more of those tomorrow. For homework this evening, number 1, memorize your fundamental loci. Memorize your fundamental loci. That quiz will be tomorrow. And just 3 practice problems to go along with those memorized loci. Page 176 to 177. Page 176 to 177, numbers 2, 3, and 8. Pages 176 to 177, numbers 2, 3, and 8. We'll look at those 3 problems tomorrow. We'll review tomorrow, and then we'll take a quiz tomorrow. So make sure you're good on how to draw the sketch and how to word the locus. All right, you are dismissed. Have a wonderful rest of your day.